Hello and welcome to the fourth part of this series, where now we will be utilizing the derivation that we found here and from the Rashford-Rice method and equation to perform a set temperature pressure flash calculation for a feed with given values of 4 moles per second of benzene, 6 moles per second for toluene, and the flash jump set at 393 Kelvin and 150 kilopascals, asking us to determine the compositions and flow rates of the outgoing vapor and liquid phases. So let's go ahead and get started. I'm going to pull up what we used last time. This is the same code or same Python or the same collaboratory note sheet that we used in the first part of this series or second part of this video. So I'm simply going to start off by putting what we know, given our knowns, right? Let's simply start off by that. So we know that the temperature is 393 Kelvin, right? We also know that the pressure is 150 kilopascals, also known as 150,000 pascals, so 150 e to the third pascals. Yeah, I'm just going to put one. And then we also know the mole fraction between benzene and toluene, right? So we're going to create a list or an array. So np dot array, which will have 0.4 and 0.6, right? Then finally, we also know the feed, right? If one is 4 and one is 6 moles per second, it should have a total of 10 moles per second, right? There we go. This is all of our nodes. Sorry, I should put a period, but all of our nodes are in and good. Now we can simply start by putting this derivation that we found here, right? We can start by writing it. So we know that z multiplied by k minus 1 divided by 1 plus v over f. So for now I'm just going to keep it a vf just so it's easier to multiply and to work out, and also k minus 1 and subtract them, right? And also, however, we want the summation of this, right? So I'm going to be np sum of this value, right? And also, we were going to want this value to equal to 0, right? We want to find when this denominator is equal to 0. So our goal is to find out and utilize the root function to make this vf as 0, right? So as you can see, we also don't know what k is. It's underlined as red, but if we go back here, we know what ki is, right? We know it's the purely saturated component in the vapor phase divided by the pressure. So I'm going to go ahead and put that into our nodes as well. So k is equal to the purely saturated, so it's just p dot pvap, right? We're using the constant temperature still, divided by the pressure, right? And we know both of those, right? Because we know the temperature, we know the pressure. So now k is all good, and we just need to say what vf is, right? Or we need to create a function so that this vf is rooted to 0. So and define a function. We'll call it rr for Rashford-Rice, and we're gonna have a vector inside of it, right? And obviously we're gonna unpack that vector as vf, right? It's gonna be the first one of these, right? And obviously we're gonna want to return this value at the end, right? Right. Get the indentation correct. Right. So we can go ahead and check if this is all good. So do root function and rr for equation, and just give an initial guess, do 0.5 for now. Right. Simply forgot a multiplication sign here, I believe. Yeah, and there we go. We have our value for the VF, right? Here we go, and now we can make this equal to VF, so we can pull that out later on. We know with the values, right? There we have it. Now all we have left to do is create these last paths so that we have all of the values that we're trying to find, right? As we're looking for the compositions and flow rates of the outgoing vapor and liquid phase, right? So let's go ahead and connect these, right? For example, we can start with VF, right? We know that simply VF is equal to VF times V, or times the feed, right? And we also know that Y is equal to K times X, right? Then for X, however, we know that, this should be a capital K, it's a close one. But for X, we have the value right here, right? So we know that X must be Z divided by 1 plus VF multiplied by K minus 1, right? Right? And then finally, for L, we know that L is equal to F minus V, right? So now we have all of our paths connected. Make sure that these are all good. So VF is equal to, okay, V must be equal to VF times F. There you go. So now we could say print V, Y, X, L. Here are our values, right? We can go ahead and make this seem real nice by giving some real values. Print, what we can do is print F, start off with the total amount of vapor moles. So moles is equal to vapor moles is equal to V, right? Go ahead and copy this and do this again, but do for the total amount of liquid moles, and this is L, right? We can do this again 2 more times. Liquid mole fraction for one, and then the vapor mole fraction for the other. And this liquid X and vapor should be Y, right? Go ahead, click Shift Enter. Oh, oops, stop the brackets. Don't know why I started off with those. Okay. Okay, should be all good now. And of course, obviously almost forgetting, we also want VF. We want the vapor mole ratio, right? Ratio is equal to VF. There we go. These are our values that we've been searching for. Thank you. Have a good day.